third law?
Section 7 is Newton's third law. Hopefully you remember what Newton's first and second laws were.
Wait, I feel like it's going to be on the test.
Newton's laws are definitely going to be on the test. Newton's third law.
Would you have to describe them or pick A, B, or C?
I don't know. I guess you'll find out when you take the test.
Oh no, I'm going to have to memorize what they say.
Yeah, you probably should know what they say. Newton's third law is here. Every force occurs as, this should say one, God, these typos, one member of an action-reaction pair of forces. And so then I break that into two parts. The two members of an action-reaction pair act on two different objects. So they act on each other. One acts on the other while the other acts on the one, okay? Two members of an action-reaction pair point in opposite directions and are equal in magnitude. So both of those parts are Newton's third law. And it is very important that you understand both of those parts and that you think about both of those parts as you are thinking about Newton's third law. The bottom here is how Newton's third law is often stated. For every action, there is an equal and opposite reaction. It's a cute and catchy phrase, but it's not very precise. This is how most people who think they know Newton's third law say Newton's third law, but it doesn't really get at what Newton's third law is actually talking about. You need to know Newton's third law as stated here. This is Newton's third law. Okay? So we're going to be working with Newton's third law as stated above, not below. All right, here we go. So we have this picture with the hammer pounding on a nail. Each force in an action-reaction pair, remember, acts on a different object. So the force on the hammer, so the hammer is pounding on the nail, right? We have the force of the hammer hitting the nail. So that is this one right here. The hammer hits the nail and the nail gets driven into the wall. But at the same time, because the hammer hit the nail is also reacting to that and pushing back on that hammer. And so therefore, there is a force of the nail pushing back on the hammer. They are an equal pair of forces, okay? It's an action-reaction pair. Because there is a force in one direction, there's a force in the other direction.
So they are equal?
Well, let's go back to what Newton's third law says. The two members of the action-reaction pair act on two different objects. So we have the hammer and we have the nail, right? The two members of an action-reaction pair point in opposite directions and are equal in magnitude.
But then how come the nail is getting driven into wood?
So that will, how come the nail is getting driven into the wood will be something that we talk about. But they do have equal magnitude, right? Equal magnitude, you can see how we've drawn that. And they are acting in opposite directions. And they're acting on the opposite body, right? So the nail is acting on the hammer and the hammer is acting on the nail. Okay? Now, this, the way that this worked out here on my screen is hopefully different than it worked out on your notes. This is a separate problem. Let me see what this is doing here. Okay, yeah. This should have come out like on a different screen. But anyway, this is a separate problem. 10,000 kilogram truck is in a collision with a 1,000 kilogram compact car. During the collision, is the force of the truck on the car greater than, less than, or equal to the force of the car on the truck? What do you think? Equal?
Yeah.
Why?
Because the two members of an action-reaction pair pointing in opposite directions are equal in magnitude.
Yeah, they're equal in magnitude. So the force of the truck on the car and the force of the car on the truck, we're talking about an action-reaction pair. So the action-reaction pair will be equal in magnitude. Okay? So that is the key in Newton's third law. You got to identify the fact that we have an action-reaction pair and they will be equal in magnitude. So in this problem, so different speeds. In this problem, we didn't even talk about speed, right? Take a look at the hammer and the nail. Was the hammer moving? Yes. Was the nail moving?
No.
Nope. So speed has nothing to do with it. Okay. Good question. All right. So we have a bullet. We normally think of the damage that the bullet inflicts on the target, but according to Newton's third law, the target will also exert damage on the bullet. So the bullet on the left was not fired, but moving our way to the bullets as we go through the progression here, they have been fired into a test target at increasing speeds. And so, like, it's the same bullet, but fired with just a higher and higher speed towards the target. And so clearly, as we increase the speed of the bullet towards the same target, the target is inflicting more and more and more damage. So, of course, the bullet would be inflicting more and more and more damage on the target as well. That's the action-reaction pair, the bullet and the target, okay? They are exerting an equal force in opposite directions on each other, action-reaction pair. Okay, so now we have this one. In the picture, we are walking. So we got this this dude, I don't know how that guy is walking, probably going to have problems later in life, but in order to walk, you are actually pushing backward against the surface that you're walking on. So like just walking on the carpet or whatever, you're pushing backward on the carpet in order to propel yourself forward. So that is an action-reaction pair. You have the force of the surface on the person, and you have the force of the person on the surface. That is your action-reaction pair there, and that is what is allowing to propel you forward. Technically, I guess you could go further and say that that is just the earth that you're pushing on, but the earth is so big that you don't even notice that you're pushing on it. But anyway, the surface and the person are your action-reaction pair. Or in part B, you have a vehicle, and it's doing the same thing. In order to propel the vehicle forward, the tires this time, instead of the feet, are what is doing the pushing. So you have the force of the road on the tire and the force of the tire on the road. This time, this is your action-reaction pair. The tire pushes backward, the road pushes forward, and that is how you go forward. So the surface, in both cases, must have friction. Otherwise, you're not going to walk or you're not going to drive. If you're on an icy road or if you're on an icy surface and you try to walk forward, you slip, right? You're trying to propel yourself forward, but you can't do so very well because your feet are sliding out from underneath you as you try to walk forward. That's because you're used to a certain amount of friction, and so you're pushing with the same amount of force, and that action-reaction pair does not have the same amount of ability to push back on you because of the lack of friction, so you slip. Or your tires on your car, same thing, okay? So your normal pushing force needs to be decreased, and that's why you're slipping. So you adjust, and then you push with less force, and then you don't overcome the friction force that is required on the icy surface, and then you can finally push yourself forward. So if we had a frictionless surface, would we be able to push ourselves forward? We wouldn't be able to move at all. We would just slip. Okay? So the person's shoes and the vehicle's tires must have friction on them for the same reason that the ground must have friction as well in order for us to move. So in both cases, the person walking and the car driving, the type of friction involved is actually static friction. Why? Yeah, go ahead.
Because the foot, right, is not actually sliding on the floor. It's just staying until it's picked up and moved again. Okay,
good. That's actually exactly right. So even though the person or the car is moving, at the contact point, the foot is not moving. And so therefore, the friction is actually static friction. So that's kind of difficult for some people to kind of wrap their heads around, but the motion that is happening is static, actually not motion at all. It's actually static at the point of contact. That's why. Okay. So now rocket propulsion. The rocket is pushing the hot gases backward, so we have the explosion that's happening inside of the rocket, and then it propels the hot gases outward behind the rocket, and that creates the thrust that pushes the rocket forward. So the action-reaction pair here is the expulsion of the rocket gases backward, which creates the force forward. Okay, so there is an action-reaction pair here. It's just a little bit different to think about. Propelling the rocket gases backward, pushing the rocket upward or forward, depending on the direction that it's going. So that's rocket propulsion for you. Okay, and then finally already, we have the small car pushing a larger truck that has a dead battery.
Man, I want to see if I can do that.
It can. The mass of the truck is greater than the mass of the car. So the car and the truck are moving to the right and are speeding up. Which of the following statements is true? Let's think about this one for a minute or so, and then we'll come back. All right, what do you think?
I said C, but I'm down.
I think it's either B or C.
C, B, or C? C?
Could be A. I don't know. I'm trying to think. I know C, but I'm thinking about A.
Well, using Newton's third law, if we're going to exert a force on an object, will the object exert a force on us?
Yes.
Yes. So this A says the truck doesn't exert a force on the car.
Well, so that's why I'm confused, because like they're acting sort of as like one body, you know, like
Is the car pushing on the truck?
yes.
Does the truck push on the car then?
Yes.
Yes. So it can't be A.
Also, but here's what I'm thinking, right? So like I have a sweatshirt, right? My sweatshirt's made out of tiny cotton fibers, right? All woven, each woven together. So if I pull on one side, they're all exerting a force on each other all the way back, right?
Mm-hmm.
It's just kind of insane to think about like things that look like one rigid body aren't actually.
Okay.
It's, yeah,
It can't be B either.
it's obviously C.
So because it's not A, it can't be E. And the car exerts a larger force on the truck than the truck exerts on the car. Again, this is just a Newton's third law situation. This is
But see,
equal in magnitude, right?
it could be B though because you're accelerating.
No. But
So,
every-
I know, it's most,
Every action has an equal and opposite reaction.
That's the cutesy phrase.
I know, that's why I said it in a cutesy way.
B and D are basically the same, just opposite order. The only possible answer is C. It's the same force.
so how come it's accelerating?
It doesn't matter.
It's just a bunch of,
The interaction force between them is equal. Okay? It doesn't matter that we're accelerating. We could be decelerating. We could be doing whatever we want to do. The interaction force between them is equal. That's Newton's third law. Okay? All right, section's over.
You actually